Hey everybody, we're going over sections 1.3, which is graphs of functions. Let's talk about it. So first thing we're going to talk about is what is the graph of a function? And it's a collection of all the ordered pairs, which we say are x comma f of x, or x comma y, where every x is in the domain of f of x. All right, let's talk about the greatest integer function. It looks like this. It's denoted by 2 brackets and then x. And the greatest integer function means that we basically take whatever number it is and we round down to the lowest or the nearest integer. So we're not rounding up, we're rounding down. And a step function is what the greatest integer looks like. It literally, as you graph it, it looks like steps. And we'll show you what that looks like in a minute. An even function is a graph that is symmetric. So far I can't spell. Symmetric with respect to the y-axis. So if you were to take a graph and fold it along the y-axis, they'd be the same, okay? And an odd function is a graph that's symmetric with respect to the origin. So let's talk about what these graphs are. So if we're talking about open or closed dots, so let's say, for example, we have a graph that looks like this. Okay, we have these, and then this is open right here, okay? And here's this, and here is this, and so on. So this tells me right here, because this is a closed dot, it tells me that value at x of -1 is in the domain. And this open dot here, since it's an open dot, it tells me that its x value of 4 is not in the domain. Okay, so the domain is going to start from -1, which is in the domain, up to 4, which is the end of the domain, but it's not including 4. How do you find the domain of a function from its graph? So you're gonna look from left to right along the x-axis for the open or closed dot, or lines that extend past it. And the values of x are valid for f of x that are in the domain. So if x makes the statement valid, it's in the domain. How do you look from the range? So you're going to look from bottom to the top of the y-axis, similarly to the domain. So what's the vertical line test? We kind of went over this earlier, but if you can draw a vertical line through f of x, where it only intersects once, then f of x is a function. Whereas if it hits twice or more, it's not a function. So let's talk about this example. Decide on whether each graph represents as a function of x. So the easiest way to find that is just draw a vertical line anywhere. And I can see if I draw this line here, it only hits once. So yay, this is a function. Whereas if I draw a vertical line here, it hits here twice. This is not a function. Okay. Let's talk about decreasing and increasing functions. So here's the deal. An increasing function is just simply if you've got some value of x that's less than the second value of x, it implies that the function of the first value of x is less than the second value of x if it's increasing, okay? And secondly, if it's decreasing, then if you've got one value of x and it's less than a second value of x, then it implies that the function of the first value of x is greater than the second value of x. And it's constant if the two values equal each other. So if it's a function and it's on an interval where it's increasing, you're going to look for x values where f of x is rising from left to right. And if it's an interval where it's decreasing, we're going to look for x values where f of x is falling from left to right. And then if it's constant, you're going to look for values, or for x values, where f of x stays the same. And here's what that looks like. If we've got a graph that looks like this, that's increasing. If we have a graph that looks like this, that's decreasing. And if we have a graph that for a portion of it looks like this flat, that's constant. So let's look at relative maximum and minimum values. A value where the function of some value is called a relative minimum means that f of a, the function of a, is the lowest point in its region. And all that means is that in that general area, it's the lowest point. So for example, if you have a graph that looks like this, I see here, this is the lowest point. So we call that a relative minimum. But here's the thing, I can see that this is going to keep on going forever. So it's not the absolute minimum, but in this area right here, it's the relative minimum. Let's talk about a relative maximum. So a relative maximum is when some value f of a is the highest point in the region. So for example, same graph, this point right here is a relative maximum because in this region, it's the highest point, but do we see that this can keep going higher, higher, higher? So it's not the absolute highest point, but in that region, it's a relative maximum. So the point which function changes from increasing to decreasing is a relative maximum. Do you see how this relative maximum went from increasing and now it changes to decreasing? Okay. And the point where it changes from decreasing to increasing is a relative minimum. So you see at this point how it goes from decreasing to increasing, and it changes. Okay. To approximate this using your graphing utility, aka graphing calculator, you're going to use your zoom or trace feature. So specifically in a TI 83 or 84, you're going to graph your function in your y equals key, hit graph, and then you're going to sit the second key and hit the trace key. When you do that, it will give you these options. It will, if you select option number 3, it will you can select the local minimum, and it will tell you the local minimum values exactly. Or option 4 is the local maximum value. So we'll talk about that in class, but I want you to have that in your notes. Okay? So suppose a function C represents the annual number of cases, and it says that there's a meaning behind, there's a minimum point of 1988, 3. That tells me if it's a minimum that the lowest point was at this X value. So we can say at the year 1998, there were only 3 cases of chickenpox, the lowest in years. Okay, so let's talk about the greatest integer function. So this, when there's double brackets here, it's denoted as the lowest integer function. That tells me if I'm evaluating f of 3.74, I'm going to say, well, f of 3.74 means we're going to round to the lowest integer. So 3.74 would round down to 3. When I graph that, here's what it looks like. When I take a value of, let's say, 1 just rounds down to 1. So that's a value. But anything more than 1 is also going to round down to 1. So it keeps going up until it hits 2. So at 2, it rounds up to 2. Okay? Oops. That was supposed to be at a 1. So when x is 1, so is y. And when x is 1.5, 1.7, 1.8, and so on, it goes all the way up until it hits 2, where the graph jumps up again. And then at 3, the graph will jump up again. So it rounds down up until this point, and then it keeps going. So you see how that looks just like steps? That's our greatest integer function. Okay, last page. Let's talk about even and odd functions. It's symmetric with respect to the y-axis whenever, if x and y is on the graph, it's symmetric if it becomes negative x comma y. If it's symmetric with respect to the x-axis, whenever xy is on the graph, it's going to become x comma negative y. And if it's respect to the origin in symmetry, it becomes negative x comma negative y. Also, a graph that's symmetric with respect to the x-axis is not a function usually, with the exception of the graph of y equals 0. And then lastly, if a function's even, then f of negative x is f of x. It's the same as f of x. And then this is a typo here. This is supposed to say odd. If a function is odd, then when I plug in negative x for f of x, I get negative times f of x. All right, that's it for today, guys. See you in class.